afternoon, and it's 8 a.m. I think in Bern,
Yes.
where our speaker, Professor Thomas Froelicher, is speaking from. I just want to acknowledge the custodians of the land in which you are all joining this meeting from. Here it's the Palawa and Muanina people. Pay respects to their elders, past, present, and emerging. So I'm delighted to introduce Professor Thomas Froelicher, who I've known now for a few years. I think he may well be known to many of you. And I'm sure that he will give a talk that will reach out and provide some excellent information about marine heat waves, biogeochemical extremes, and compound events. Thomas Froelicher is a full professor at the Climate and Environmental Physics Division at the University of Bern and leads the Ocean Modelling Group. His research focuses on marine ecosystem carbon-climate interactions with a particular emphasis on ocean extreme events and their impacts on climate and on marine organisms and ecosystem services. He earned his PhD in physics from the University of Bern and completed multi-year research stays at Princeton University and ETH Zurich. He was the lead author of Chapter 6, Extremes, Abrupt Changes and Managing Risks in the IPCC Special Report on the Oceans and Cryosphere in a Changing Climate, and the Second World Ocean Assessment. He's also contributed to the 5th and 6th assessment reports of Working Group 1 and 2 of the IPCC, and he's currently a member of the CLEX Marine Heat Waves Research Focus Group of the World Climate Research Programme. So without further ado, I might pass over to Thomas.
Yeah, thank you very much for the kind introduction, Neil, and for meeting you all. It's a great pleasure. And also thank you very much for the invitation. Okay, let's try to share my screen. Can you see it? I hope so.
Yes.
Okay, excellent. Okay, today I'm going to talk a little bit about the marine heat wave, but then we'll also actually move towards more biogeochemical extremes in the ocean and compound events. And I will talk about the drivers, about the changes, and some potential impacts of these compound events on marine life. But let me start really just quickly broad in a sense. So if we go up to space and if we look back to the Earth, actually the Earth appears as an almost perfect aquaplanet. In fact, the ocean covers 71% of the Earth's surface, but the ocean is not only a big reservoir for water, it's also a big reservoir for heat and carbon. So in fact, the ocean takes up about 90% of the excess heat, which accumulates in the Earth system due to the increase of greenhouse gases. But the ocean also takes up about 20 to 30% of the anthropogenic carbon we emit into the atmosphere due to the fossil fuel burning and land use changes. And the ocean obviously also provides food and other services to more than 1 billion people on Earth. So this huge climate mitigation service the ocean provides to us comes also at profound alteration in its physical and biogeochemical state. So for example, the uptake of heat obviously leads to warming of the ocean. And here you see sea surface temperature projections from CMIP5 models into the end of this century for 2 emission scenarios. So the ocean has warmed at the surface by about 0.8 degrees Celsius and is continued to warm into the future. The ocean, due to the uptake of carbon, actually gets more acidified. So that means when the CO2 is taken up by water, actually it reacts to carbonic acid, and that dissociates then to bicarbonate and releases hydrogen ion. But it also leads to actually a decrease in the carbon ion concentration. But overall, we have more hydrogen ion in the ocean water, and that leads then to a decrease in the pH, which you can see here. So the pH has decreased by about 0.1 units over the historical period and is projected to continue to do so in the future. And due to the uptake of the excess heat, actually the ocean is also losing oxygen. due to, there are different effects which actually impacts oxygen. The first one is just the pure solubility effect. If the ocean is actually warmer, then the water can actually hold less oxygen because of the solubility, which is decreased. But because of the uptake of excess energy, the ocean also gets less ventilated, and that leads then to a less supply of oxygen-rich water to subsurface, and therefore to a deoxygenation, especially at subsurface layers, which you can see here. So the oxygen concentration has decreased in that particular layer, 100 to 600 meters, by about 1 to 3% over the last 50 years, and is also projected to continue to do so. But I think one important thing, and we know that quite now for a long time, that actually we see these gradual changes over the historical period and also for the future, but we have somehow realized that these gradual changes are somehow punctuated by so-called extreme events. And I will give you just one example. So that's a satellite image from the Mediterranean Sea in 2022. But I could actually also use a satellite image from 2023 in summer. It was similar. So the Mediterranean Sea was actually more than 5 degrees warmer in particular regions like in the northwest than usual in summer 2022. So these so-called marine heat waves are of particular concern, and they have actually happened all over the place in the ocean recently. So that's a relatively old compilation we did a few years ago, where we actually compiled the most impactful marine heat waves which have been documented in the literature. We put them on a map, but there are now newer versions actually available. So I refer to the Oliver paper, for example, where you have a much nicer actually picture of the different marine heat waves. But anyway, so we had in the Mediterranean Sea already in 2003 a big marine heat wave with large impacts, Northwest Atlantic in 2012. Then in the Gulf of Alaska 2016, we had this huge Northeast Pacific blob. And then we had several marine heat waves around Australia, but also in the Yellow Sea. And I think these marine heat waves have really caught the attention of us researchers when we actually saw then the impact which they can cause. And you may know that very well from the Western Australia marine heat wave in 2010 to 2011. So here in the bars shows you the temperature anomalies, and in 2010 to 11, the temperature anomalies were quite high. So temperature anomaly up to 3 degrees. And usually this area there is actually dominated by kelp forests, but when the marine heat wave hit that region, it actually was replaced, the kelp forest ecosystem, by seaweed turf. And it hasn't really recovered yet from that disturbance since then, since about 10 years ago. So these marine heat waves can really largely disrupt marine life in the ocean, but they can also affect weather over land. So for example, they can lead to heavy precipitation events over land, as the Tasmania marine heat wave actually did, but they can also lead to drought events and heat waves over land. So they are, I would say, quite important, or they emerged as an important factor to actually really understand also extreme events over land, but certainly for actually understanding marine life and their responses to climate change in the ocean. And as you all know, actually, that trend of sea surface temperature increase hasn't stopped, especially in 2023. We had really unprecedented sea surface temperature since the beginning of March, and that actually still continued to do so. So the black line here, so that's basically the seasonal cycle from January to December since the start of the satellite period. And you see 2024 is really the highest sea surface temperature average globally since the start of the record. And especially in the North Atlantic, the sea surface temperature were really high. And there were some claims that actually the models cannot really reproduce these global sea surface temperatures. I would argue they can, but I think we can discuss that maybe during the Q&A session about the potential hypothesis here, why that sea surface temperature is so high in 2023, and if the models can actually reproduce that. So that brings me to the outline. So first I will talk a little bit about marine heat waves, the driving factors, trends, and attribution. Then I will actually go to ocean biogeochemical extremes, so ocean acidity extremes and low oxygen extremes. And I actually think so far we have probably overlooked a potential serious problem and the potential important driving factor of big impacts in ecosystems. And then I will also quickly talk about potential impacts of extremes on fish and fisheries. Actually, there are some conflicting results right now in the literature, and I try to reconcile them a little bit. Okay, so what is a marine heat wave? I will just quickly, briefly touch on that. So in IPCC, we came up with, or the IPCC author team came up with the following generic definition. It's actually a period of extreme warm near sea surface temperature that persists for days to months and can extend up to thousands of kilometers. I think that's fine, and that gives a generic definition, but it's not really useful if you want to do quantitative statements or if you want to do some analysis on sea surface temperature anomalies, because then you need to make some choices. And just to quickly go through what actually choices needs to be done to actually come up with a quantitative statement, for example, how heat waves are actually going to change. So you need to define your baseline period, if it's fixed or shifting with time, or if it's periodically updated as the WMO actually suggests. Then you need to define your threshold. Is it a relative threshold or is it an absolute threshold? But often these absolute thresholds are unknown. But they would actually, so if we have different ecosystems, they would be probably preferable to be used, but often we do not really know the absolute thresholds we should use to actually say when actually impact occurs. Then we need to say when we choose a relative threshold, if it's annually fixed or if actually the heat wave can actually also occur in winter time and not only in summertime or in any season. And then often a temporal criteria is used. For example, in the hop day definition, they use a duration criteria of at least 5 days. Others don't do that. And then if we have done all these different definitions or applied these different criteria, then we can actually characterize the marine heat wave, the frequency, the duration, intensity, spatial extent, or the depth structures. So especially in the ocean, we often also look at the depth structures of these marine heat waves. And just to mention, recently there was a bit of a debate about the baseline period. And Alex and Gupta, I borrowed that term from him. It's the battle of the baseline. Actually, there were two Nature comments about how we should actually define the baseline when we talk about marine heat waves. So basically, the left paper was suggesting that we actually should always use kind of a shifting mean or detrended baseline, and we should also always define the heat wave relative to present day or nearly present day conditions. Whereas on the right side, we were more actually, we were more suggesting using the fixed pre-industrial or a fixed baseline, because when we want to know the total risk on ecosystem, actually the mean warming trend is also important to understand. I just want to highlight that. I don't want to go in too much detail here, but I think it's important to remember which baseline we actually apply to understand how the heat waves will actually change in the future. But if we want to look at the local drivers or the regional drivers of a marine heat waves, it's good to remember what are the spatial scale and the temporal scales of these heat waves. So that's basically a figure from Neil's paper in Nature Communications in 2019. So the spatial scale of a marine heat wave is about 10 to roughly 1,000 kilometers usually, and the temporal scale lasts from about 5 or days up to a year. And what are the processes which leads actually to SST variations on these different temporal and spatial scales? So there are different local processes which affect the mixed layer temperature budget. So like eddy processes, vertical processes, then air-sea heat exchange, which can change the temperature, ocean advection, and wind stress. And if we want to understand usually the temperature changes or the local processes, we often actually build a mixed layer heat budget. It's basically just the temperature tendency in the mixed layer, which is equal to the horizontal advection term, horizontal mixing term. Then we have vertical mixing, the air sea heat flux with all the different terms here. And then we also have entrainment of cold or warm water at the base of the mixed layer. Of course, there are also teleconnection processes and persistent features which can actually lead to SST variations like Kelvin waves or Rossby waves, or atmospheric blocking or jet stream in front. Then we have these large-scale climate modes which can actually modulate sea surface temperature like ENSO or IOD or the IPO. And then we also have long-term climate change, which actually changes then the temperature of the ocean on longer time scale. When we then look at the local processes, and we did that in the GFDL ESN2M, so we looked at the temperature tendency terms of sea surface temperature during the onset phase of a marine heat wave. So basically, when the temperature crosses the 90th percentile until its peak temperature. And we looked then what are the main factors which lead to the SST change when the SST is really high until its peak. We see here during the onset phase, especially in the mid to low latitudes, it's especially the air sea heat flux anomaly. So enhanced air sea heat flux anomalies or reduced air sea heat outgassing, which leads to really to the buildup of the marine heat waves, at least in that model. And reduced convective vertical mixing actually leads to somehow a counterbalancing SST, so to a relative cooling, but overall the air sea heat flux actually wins, whereas in the equatorial Pacific, it's mostly the local mixing and the vertical diffusion, which actually leads to the buildup of SST. During the decline phase, actually we have mostly the air sea heat flux, which also leads then to the decline of the SST. Heat wave, which we have sampled, and that's then a composite. When we then look at different seasons, we see that the air sea heat flux really dominates in both seasons, in summer as well as in winter. But actually, it's in winter, it's mostly driven by the reduced latent heat outflux from the ocean to the atmosphere, which actually leads to the buildup of SST, whereas in summer, it's also short wave radiation, mostly driven by less cloud often during the buildup of marine heat waves, which leads actually to the buildup of this SST to the peak SST. But I have to mention that actually we mentioned that in that paper that different types of marine heat waves have distinct driver combinations. And there is actually a large variability, even in the same regions, of the drivers, which can lead then to the buildup of the marine heat waves. So when we look at the satellite record, yes, before I go there, I think I also included a little bit of knowledge gaps, where I think we still have a lot of knowledge gaps, actually, which we should make progress in the near future. I think we understand relatively well the surface processes, which leads to the processes which leads to the surface heat waves, but that's actually at subsurface, the processes are often poorly understood. And I think small-scale coastal processes are often also unresolved in those models we usually use to look at the driver processes, at least at the global scale. When we look then at the satellite record, and we only look at the 300 largest marine heat waves, and here we use the fixed 1982 to 2018 baseline, we see that actually the marine heat waves have approximately doubled in frequency and have become more intense and longer since 1982. And you see here the blob, it was really the longest marine heat wave ever on record. So the 2023 is actually not included here. But actually, before 2023, the blob was really the longest marine heat wave on record. So we were wondering actually if these red highlighted marine heat waves, which I have also introduced you on the map at the beginning, are they actually already caused by human-caused global warming? Or is that just natural variability which have caused those? And we do not really need the long-term global warming trend underlying the SST variations, which leads to these heat waves. So we have tackled that question by using an event attribution approach. So it's a probability-based approach. I think first developed by Peter Stott and Miles Allen. So what we calculated is actually the fraction of attributable risk. It's 1 minus the probability that the heat wave occurs in a pre-industrial world, so counterfactual world, and the probability that the heat wave occurs actually today. And to come up with a counterfactual world, we actually used the CMIP type of models, and we also tested the models if they can actually reproduce the heat waves for the right reason. And we only included the models which actually can do that in the analysis. And then we looked at these 7 typical marine heat waves here on the top right. And we actually did this event attribution for the intensity for the different heat waves, but also for the duration. And if this far value is close to 1, that means the heat wave is most likely have only been occurred due to human-caused global warming. So it was really unlikely that such a heat wave would have occurred under pre-industrial conditions. And just to highlight one, so if we take this blob, which had the intensity of 1.56 degrees averaged over the full area, and also a duration of about a year, the far value was close to 1 or basically 1. So that means such an intensity and such a duration of the blob was only possible due to human-caused global warming. And that applied to many, actually, that statement applied to many heat waves we actually have investigated in that paper. It didn't apply to the Southern Ocean heat wave because the models are too uncertain and not really up to the task to really investigate in the Southern Ocean.
Excuse me, Thomas. Thank you. This is really going great. But yes. We don't know what happened this time, but we've got a message from Zoom that the meeting will be shut down in half an hour.
Oh.
Jara will send an email to everyone with new links. So I just wanted to give the heads up to everyone. If that happens,
yes,
just check your email and reconnect, and we'll continue the seminar.
Sounds good.
So sorry for the interruption.
Yes.
Hiccup. Okay.
I will just continue and then we will see.
Yeah. Just continue and we'll tell you where you got cut off.
Sounds good. Okay, so the idea, so if we go to the weather attribution team and look what kind of extreme events they have attributed, often actually the ocean is not really dealt with. I think one idea would actually be to operationalize actually this near real-time attribution of marine heat waves, which should be actually feasible, I think. But at the moment, actually, attribution studies for biogeochemical extremes or impacts are currently missing, which I think it's a large knowledge gap. Yes, so when we then look into the future, when we use these climate models and we define the marine heat waves with different extreme event threshold, 90% and 99% and so on, and we can look at the number of marine heat waves per year. When we then look at in a 1 degree warming world, actually the number 2 degree warming world and 4 degree warming worlds. So here I use a fixed pre-industrial baseline, and basically what that means, and one in a 100-day event especially it doesn't really warm up that strongly, at least in a transient ocean under 2 degree global warming in these marine heat waves. When we compare that to land-based heat waves, we see the marine heat waves actually change more dramatically in terms of number of heat waves than land-based heat waves. We look at the PDF of SST variability here on the right and temperature variability over land on the left. We see that the SST variability is much smaller than the land air temperature variability. So even though the temperature over the ocean is actually changing less than over the land, we see a more overproportional increase in the frequency of marine heat waves due to this narrow distribution of SST variability relative to terrestrial temperature variability. So when we look then back to the blog, just give you one example from that paper we published actually almost annually or on decadal basis if global temperature rises by 3 degrees, which is quite concerning when we